Right, there's a series of equations which I refer to as cake. So these are the constant acceleration kinematic equations. And the key thing there is constant acceleration. If acceleration is not constant, then calculus most likely is involved. I mean, there are some shortcuts that can be taken if you're comfortable enough with it. But for the most part, if acceleration is constant, you don't have to use calculus because we're about to derive those equations. Now, there's four primary cake formulas. There is a fifth one that some textbooks use, but not many of them do it. So why don't we just start out with the derivation. So we know that acceleration is the time derivative of velocity, or in dot notation, v dot. And this is by definition. That's how acceleration is defined. And so, therefore, acceleration times dt is equal to dv. We integrate both sides. Now, as we integrate it, we are taking it from some initial velocity, to a final velocity, and acceleration from some initial time to some final time. And so as we do the derivative, we end up with acceleration, because that is a constant, it basically factors out from ti to tf. dt is equal to v final minus v initial, which is acceleration times, in essence, t final minus t initial. This right here is the change in time. And so what we end up with here is vf minus vi is equal to acceleration times this change in time, however much time takes place going from the initial to final velocity. And bringing this over to put it in more traditional form, we end up with the final velocity is equal to the initial velocity plus acceleration times delta t. Now, there are a couple other forms of this that you might see and also there might be some other ways that I write it as well. I sometimes use I for initial, or I think I do it more often than not, but sometimes I might, instead of using an I, I'll use a 0. And sometimes I will use an O, which looks a whole lot like my 0. And so O for original, or 0 for, time is equal to 0. And another form, this delta t here, oftentimes if you consider the clock starts at the initial time. So if the initial time is 0 seconds, or whatever units you happen to be using, then delta t, which is tf minus ti, becomes just tf. And since I'm only dealing with one time here, why not just make it time? And so in this format, you might also see v is equal to vi, or vo, or v0 plus at. And so this is another form of the same formula right here. Which way I write it really depends upon my mood at the time. That is the first cake formula. Now, you won't find any textbook, I think, refer to as the cake formulas, as well as I'm referring to this as the first one just because it's the first one I derived. And it's probably the first one that every textbook derives, but it's not like Newton's formulas where the first one is always the same one. I know, as we've just already derived, vi is equal to v naught plus at. Let's put the vector symbols onto it. And I know that v, velocity, is equal to the first derivative with respect to time of position. And therefore, dx is equal to v dt. And so dx is equal to v naught plus at dt. And so dx is equal to v naught dt plus at dt. And of course, we're going to integrate next. Now, this is the initial velocity. This is a boundary condition. It is constant, so it is going to factor out. Acceleration is constant because these are constant acceleration formulas. This is one of the premises. And so I'm taking it from some initial position to a final position. I have time from some initial time to some final time, and then this from initial time to final time. And so we end up with the change in position is equal to v naught times the change in time plus 1/2 at squared from some initial time to some final time. And again, using the idea that the initial time is equal to 0 seconds, then this becomes the change in position, or otherwise known as displacement. So this is displacement, or change in position. It means the same thing. Matter of fact, I think there's a master set either for 151 or 251 where I ask for what is the displacement of his problem, and then I ask for change in position of the problem, and not everyone always puts down the same answer. So this is V naught T plus 1/2 A. I guess this T final becomes T under that situation. 1/2 A T squared. And so the second one derived right there. So if I have velocity versus time graph, if acceleration is constant, recognize then dv dt is constant, because acceleration is dv dt. And since it is constant, that means I have a constant slope. So that's basically what my velocity time graph looks like. It could be sloped down, could be flat. It's a straight line going in some orientation. Since velocity is dx dt, that means dx is equal to v dt, or the change in position is equal to, well, the integral of v dt. We just went through that over here, and this is just the area under the curve. So the area here is the change in position, or the displacement. It doesn't tell us what the position is unless we know what the initial position is, or the final. We need to know some piece of information about some starting point to get the actual position, but it tells us the change in position. So if I have my graph here of velocity versus time, and this is some initial velocity, that is my final velocity, then my area here would be, as I said, by change in position, well, that's going to be the area of this rectangle plus the area of the triangle. Well, the area of the rectangle is length times width, so that is V naught times time. My triangle here is 1/2 base times my height. Well, that height right there is, well, I know that the slope is the acceleration, and the slope is the rise right there, which I'm just going to call n for the moment. So that is n over time, and so therefore that rise right there, n, is equal to a times t. So if I plug that into here as the height, so a times t, I end up with v naught t plus 1/2 a t squared, which is the exact thing that we just derived. Now another way of looking at that, if we look at the mean value theorem, means that if I have some function here that there is some average value of v such that the area under the curve, so the area of v dt, is going to be equal to this average value. Let's do that a little bit differently because there's too many lines there. Put a little avg, the average value times time. And so that the average value is equal to the integral of v dt divided by t. Officially, it's the integral of dt. So from t initial to t final, let's just make it from 0 to t and from 0 to t. I also want to point out here that in math class, at least the way I was taught, is that having the differential here and have this as the same letter as one of the boundary conditions, one of the limits of integration, is a huge taboo in math. In physics, we don't care, because we know that those two t's, this is the variable t and that is a specific time t, that we just don't happen to know what it is. Now the average here, this average, well, if that is straight here, this average is just the average of those two numbers right there. And so my average value is just my initial value plus my final value divided by 2. And so my displacement, therefore, is just equal to v naught plus vf over 2 times t. And so what we now have is, here's the first cake, number 1 cake. We have, this is the second derivative of the second time I derived it, but this is number 2 cake. And here is number 3 cake. Obviously, based on what I said earlier, there's one more to go. So why don't we take our formulas here? I know that V final is equal to V initial plus AT. And you can already see that I'm flipping back and forth between my subscripts here. Delta X is equal to VIT plus 1/2 AT squared. And delta X is equal to VI plus VF over 2 times time. I'm going to take this delta X and have a space in there for a reason. VI plus VF over 2 times time. And the math people tell me that as long as I multiply both sides by the same thing, I'm good to go, as long as I'm not multiplying both sides by 1/0 or something like that. So on this side, I'm going to multiply times acceleration. And on this side over here, I'm going to multiply times VF minus VI over t, because that's what acceleration is. Acceleration is constant, so therefore I don't have the derivative here. It's just VF minus VI over t. So now let's cancel out some stuff. That t and that t cancel out. I'm going to multiply both sides by 2, so I get a 2a dot delta x. There is a dot there. This is a very specific notation. This is known as a dot product. And over here, since I did a dot product on this side, I'm doing a dot product on that side. So I end up with VF plus VI dot VF minus VI. Notice I flipped the order around here. The commutative property of addition holds for vectors. And the commutative property for dot product multiplication of vectors holds. The other type of multiplication is cross product. It does not hold. The commutative property does not hold. There's a minus sign that gets thrown in there. So now I'm going to FOIL. So I have VF dot VF minus VF dot VI plus VI dot VF minus VI dot VI. So just FOIL. These two right here, I've already commented that the commutative property holds. Those will cancel out. VF dot VF, that is just VF squared. Notice that the vector symbol has disappeared. And this is VI squared. Oops. And that is equal to this. And so now I can write that VF squared is equal to VI squared plus 2, if I multiply that, add that to both sides, and then flip the equation around, 2a dot delta x. That is the number 4 cake. And so there's the derivation. And I guess a couple additional comments. One, dot product. When you're multiplying vectors using a dot product, it cares about parallel. So if I have a vector A here and a vector B here, I'm multiplying whatever component part of A that is in the direction of B times B. So let's make B longer. And so I'm going to break A in 2 components. I have this part that's going this way and a part going that way. And what I'm going to do is if I do A dot B, I'm going to multiply the magnitude of B times the magnitude of the part of A in the direction of B. So if that angle there is theta, this becomes B times the part of A in the direction of B, which is A cosine theta, which is AB cosine theta. If I'd gone the other way, if I'd done B dot A, so let's draw them up again. A and B, and this angle here is theta. I want to multiply, I break B up into components. So I multiply the part of B that's in the direction of A times A, so this becomes A times the part of B in the direction of A. Well, that's a right triangle right there. And so this becomes B cosine theta, which is AB cosine theta. And again, so the commutative property holds either way that you're doing it. And also noting that a dot product produces a scalar. So dot products are also known as scalar products. This is one of the reasons why the vector symbols disappeared. So dot product is the same as a scalar product, as opposed to the cross product, which is a vector product. And officially between us, it's an axial vector product or pseudo vector product, but it looks and smells the same. Taste is a little bit off. So if I take, just one more comment on dot products, if I take a vector and I do a dot product with itself, so any vector A dot A, well, since it's completely in the direction of itself, this would be the magnitude of A times the magnitude of A times the cosine of the angle between them, which has to be 0 degrees or radians, which just becomes A squared. So a dot product of a vector with itself produces just the magnitude squared. And that's why we had VF squared and VI squared.